Today, we're talking about Lenz's law. So, we've already seen it a few times, and I know I mentioned a lot of names. I would not concern yourself with memorizing names. I like to be able to say something that someone can be like, Wikipedia. It's kind of like when you see one of those superhero TV shows, and someone has a last name, you're like, ooh, that guy has a last name. I'm going to Wikipedia this guy and figure out what his superpowers are. Same idea here. So when you hear Lenz's law, you can be like, oh, it's Lenz with a Z. You can go to Wikipedia and search up what it is, how it works. Not that I won't tell you, but you should always have a questioning attitude. Suspicion. So Lenz's law, that is a terrible epsilon. So we have an electromotive force equals negative d phi dt. So we've talked about this a few times, but I've never really kind of formally discussed it. So what this is saying is that you'll have an electromotive force, basically a voltage, created opposing a change in flux, where flux is the magnetic field times the area. Flux can be anything times an area. This is actually just magnetic flux, so I should probably have a little b there just to signify that this is magnetism. So the easiest way is probably just to go through an example. This will not be a particularly formal example. This will just be here's kind of the general idea example. So we have ourselves a circle. Whoop, whoop. It's going to be made out of copper or gold. They both conduct. Though I am not going to invest in a gold circle even on paper or electrons. And then we have let's say it's in a magnetic field. And the magnetic field is into the board. That's how the little arrows, it's like when you see like arrows and these are little feathers at the end. Okay. And it's inside too, but I'll draw a couple inside. And then what happens, let's say that this is, 2-meter circle. And this circle, zoom in, is actually moving in at some speed v. And this speed v is 2 centimeters per second. So 2 times 10 to the negative second meters per second. The only reason I wrote that on the outside was because there wasn't enough room on the inside. And let's say this magnetic field here is 2 times 10 to the negative second Teslas. And the question is, what's going to happen with this shrinking circuit, or this, I guess it is a circuit, circle, in terms of EMF, voltage, etc., etc., etc. And so for this, we'll do Lenz's law. And the way I do a lot of these problems, they all kind of have the similar rhythm to them. So you'll say that, start with EMF equals negative d flux dt. And the first thing you kind of want to know is which direction is the flux going. And there's a couple ways of going through that. So the first way is looking at the formula and saying, all right, so we have an EMF, which will create a current. And this current will oppose, that's the negative sign, the change in flux with respect to time. And so you can say, all right, so our flux, which is magnetic field times area. So our flux, I'm going to say current, is into the board and getting smaller. Since the flux is magnetic field times area, since the area is getting smaller, the flux is getting smaller. So, I know, too many colors. So this is going down. And so there's going to be an opposite reaction. I'll call this the flux induced, causing the, I'm going to draw an arrow saying that this kind of implies, not saying equality. So the induced flux will be up. And so what that's going to say then is we're going the circle will create a EMF, which will create a current, which will then reinforce the magnetic field that's going down. So we have the flux going down, so this wants to create a flux going up. And by down, I mean opposite of what it currently is. And so to do this, it's going to want to create a current around the loop. So I'll say maybe an I. And for it to create a magnetic flux that reinforces the current one, it's going to have to go into the board. So it's going to create a flux going into the board, which means that the current has to be counterclockwise. So, and I know this kind of sounds convoluted, there's a certain rhythm to it. We'll go through it. So the current flux, magnetic field times area, is going down. That is the current. I shouldn't use the word current because that sounds like electrical current. Actual, real time, now. The external magnetic field times the area, which is lowering, is causing the flux to lower, which is going to cause an induced flux to rise. And this is all with respect to the in the board direction. And to create an in the board direction, wait a second. It's going to create a current going in the clockwise direction. I know, I said counterclockwise. So you do the right hand rule, wrap your fingers around the direction of the current, thumb points the direction of the magnetic field. And so what this is doing is it's creating a stronger magnetic field into the board. And so what it's trying to do then is, so you have your flux, which is magnetic field times area. The area is going down. That's just part of the loop. It's external force crushing it. And so to mitigate that fall, it's going to try and create a magnetic field. It's going to try and raise the magnetic field. And the magnetic field due to a loop is mu naught I over 2R. And so it's going to raise the current, this part right here, in an attempt to mitigate the drop of that magnetic flux. That's one way of thinking about it. We'll talk about another way in a second. So the idea here is it's going to create a clockwise, I know I said counterclockwise, it's going to create a clockwise current as this circle is shrinking within a magnetic field. And that's due to the change in flux. Okay. Whoop, whoop. Do some calculations here to find so we can find out the magnitude. Click, clack, clunk. So negative change in B times A over dt. So here we're going to have to use the product rule. So this is, put a negative sign out here, make a bracket, change the magnetic field with respect to time, times area, plus magnetic field times change in area with respect to time. We know that the magnetic field in this case is constant. So this guy goes off to 0. And we are left with negative B dA dt, which we know is negative B dt of pi r squared, because that's the area of a circle, which equals, whoop, let's see here, negative B dt, I don't know, 2r times pi times dr dt. I know, I should have used a small r there. There you go. That part disappears. So we're left with negative b 2 pi r times dr dt. And based on our initial assumptions here, we said that B was -2 times 10 to the negative second Teslas. I'm going to leave off the units. 2 pi, we said it was initially 2 meters. So we're only looking for the current at time t equals 0. And then we said it was 2 times 10 to the negative second centimeters per second squared. So here we would have 2 pi r. I could leave that as r. Nah, maybe. Yes, I will leave that as r. So this would be 2 times 2 times 2 times, so it would be negative 8 pi times 10 to the negative fourth times whatever the radius of the circle is. And this would be volts. So you might think that, wow, that's not a lot of volts. Well, that's kind of sort of true. So if we do at the electric field, the voltage at time 0, the radius would be 2 because it hasn't had time to shrink down yet. So we then have negative 16 pi times 10 to the negative fourth. And even though it doesn't seem like a lot of voltage, and it's not a lot of voltage, if you just have like a copper wire, it can be a big deal because then your resistance is very small. And so current equals voltage over resistance, voltage over 0, and then you get something really big current. So you can get, just because you have a small voltage doesn't mean you can't have a really big current with it. So that can be a risk with that. Okay, and that's just the idea. Magnetic field, circle, you shrink your circle due to Lenz's law and math, you're going to have an induced voltage, which will create a current. Now, one of your first thoughts is, okay, if we have an induced voltage here, can we model that with a battery? We have to have like a high potential side and a low potential side. Can I just draw like battery? Where would the battery go here? I don't think you can really look at it that way. I like your thought process, but you really can't look at this as, all right, we have a battery here, the charges flow from the high potential side to the low potential side. This is really part of a bigger picture. Magnetic fields don't, okay, I'm going to say magnetic fields don't exist in a vacuum, but not like a, that was a terrible way of phrasing. Magnetic fields don't exist on their own. So the idea here is you might have like a giant solenoid on the outside, and this solenoid is what's creating this magnetic field. And so the force that you're using to create this current, it comes from the magnetic field, which is coming from a solenoid, which is coming from current running to the solenoid. So you're kind of transferring energy from another source that's unseen and just assumed in this problem to your loop. And that's why you can't really visualize it as, all right, we have a battery here on the loop, because the motive force, electromotive force, if you will, is actually from an external current source. So hopefully that gives you a little bit of comfort. So the other way that we can look at how to find the current, I'll erase my terrible error of, oh no, it's still there. There we go. Of which way the current goes is we remember to calculate the, delete these guys. I'll leave Lenz's law there. If we want to find the force on a charged particle, we would use force equals Q times E plus QV cross B. And in this case, we're saying electric field is 0. And I'm going to break the loop up into 4 parts. So I'm looking at these small sections right here, which I'm going to approximate as just straight wires. There we go. And if we look at these, and I'm going to say that there's a bunch of free-floating positive charges. I know they're actually free-floating negative charges, but mathematically it's just easier to work without negative signs. So what's happening then, cyan. Since the radius is shrinking, that's equivalent to saying that this bar is moving to the left. And we have a magnetic field here of going into the board. Okay, maybe one more. Yep, that's good. And so what we do then is that we look at this portion right here. We have charged particles moving in a magnetic field. So if we look at this, we're going to have force equals Q, V this direction, times B, which is into the board. And so we're going to get down. A force down. I know, you're seeing it in the camera, it's probably looking backwards. You're like, what? Why is it using the left-hand rule? Yes. FQ, V cross B, and we're going down. And so there's a force on these individual positive charges going down. But then if we look at the other side, over here, we have V cross B, force going up. And just to kind of reassure you that I'm not pulling some crazy magic trick, so nope. Just for logistical purposes, we are going to do the bottom one. There we go. V cross B. All right, yep, to the left. So we have V force this way. And I'll let you just assume that the top one then is to the right. And the idea here is then we're getting this clockwise motion of current. And this clockwise motion of current is basically what Lenz's law says we're going to get. So there's a way of looking at it where, all right, this is the magnetic flux. This is how the magnetic flux is changing. The induced magnetic flux will be in opposition to the change. And then to create that opposition, this is what the current would have to be. The other way is looking at it in terms of, all right, this is going to be the force on the individual charges within whatever structure we have. And then I'll go around. The advantage of looking at things in terms of flux is that you actually have to calculate how much the magnitude. That kind of saves you a step. And it gets your mind in the right direction. But this way also works well if all you're looking for is, all right, which direction is the current moving? All right. So I'm going to erase these guys real quick. And we're going to look at some of the problems that we're going to get. Magnetic flux is pretty big on the AP exam. You can really demonstrate a lot of knowledge in a relatively small question using Lenz's law and magnetic induction. And so you're probably almost guaranteed to find at least one problem like this, like a free response type problem like this on the AP exam, just because there is so much knowledge that can be demonstrated that for them asking you a relatively simple question, you can show a lot of knowledge and it makes a good test question. Okay, one little problem, or one sec. Okay, so here we have a Lenz's law style problem. Ooh, a light bulb. The long straight wire illustrated above, right here, carries a current I. The current varies with time t according to the equation I equals I naught. Okay, so you have the initial current and then minus a certain amount of that current for over a period of time. Okay, and we'll assume that time is positive, where I and k are positive constants and I remains positive throughout the time. Okay, so I'm going to draw a quick graph here. You don't have to draw this graph, but you should mentally draw it drought. So you have something where you start up high, you go down, has a slope of negative k, and it never quite reaches 0. So here's time initial, time final, and here is current. Positive at the time. The bottom of the rectangle loop of wire is width b, okay? And height a, okay? Is located distance d, okay, above the wire, with the long wire in the plane of the loop as shown. Okay? And they say long wire, so we can assume that it's the magnetic fields are circular around the wire. Long, i.e. infinite. A light bulb with a resistance R, check, so it's just a resistor, is connected in the loop. Express all algebraic answers in terms of given quantities and fundamental constants. Indicate the direction of the current in the loop. Okay, so we hear current in the loop, we're going to think of Lenz's law. So I'm going to erase Lenz's law just because I don't like the way that one is written. Ooh, red. So, whoop, whoop. Flux, electromagnetic force equals negative d flux dt. And I'm going to write this out just a little bit more. I do actually recommend doing it this way on the test because it helps keep you honest. I like to say that I always get the right answers, but the problem is I also get the wrong answers a lot. And one way to kind of make sure that you can weed out the wrong answers is to be very explicit in what you write out, to know what you're doing, so to speak, to not take too many shortcuts, which I am guilty of. Okay. We know that the area of the rectangle is constant, but the current through the wire is going down, so the magnetic field through the area will be changing. So this will give us negative dB dt times A. And I'm going to write down here B of a line equals mu naught I over 2 pi r. And so at this point I'm like, all right, should we just go and find the flux? Or should we, because you're probably going to be asked to find everything, which is basically what is the current going through the wire loop. And it's one of those things you have to be careful about finding everything, when the question might be like, hey, here's this big problem, find the small easy portion and then just move on with life. And if you spend all your time trying to find everything, then you kind of get stuck with, oh, I did all this extra work and now I'm running out of time and I'm going to fail. You guys won't fail. I believe in you. So this is the point of time when I would read the problem and be like, all right, this is how much I'm going to solve. And then go back to the problem and try and solve it. Okay, so they want its direction of the current. They want the light bulb gets dimmer or brighter. So if the current is going down, then the light bulb is going to get dimmer, because all the energy to light the light bulb is basically coming from this wire. Determine the magnetic field at t equals 0 to the current at a distance r from the wire. Okay, so that's probably the equation we just wrote down. Derive an expression for the magnetic flux. Okay, and that's going to be interesting because this is not going to be a uniform magnetic field. Like the magnetic field at this part of the wire is going to be different than the magnetic field at the top of the wire, just because it's a radiance dependent from the center of the wire. Derive an expression for the power dissipated in the light bulb. Okay, so the power dissipated in the light bulb, when you never think power dissipated in a resistor, you should think I squared R losses. So what that's saying is find the current in the loop. And this is kind of stepping you through the process. So instead of it stepping me through, I'm just going to try and solve as much as I can and then match it up as required. So I will dance to my own drummer, so to speak. Okay. So we have, this is the equation of a line. And so if we do dB dt, the reason I want to find dB dt is because up here we need it. So magnetic field of a line will be, so mu naught and 2 pi r will be constant because they're time independent. But I will change. It will be di dt. And then di dt, we know that I equals, what is it, I naught minus kt. I naught minus kt. I naught minus kt. So di dt, I know it feels like we've taken like 6 derivatives by this point, will be negative k, because that's a constant, goes to 0, and then t goes to t0 times 1, which basically means it disappears. So this gives us mu naught over 2 pi r times negative k. Okay. Get rid of that line. So now we have, that is dB dt. Now, so then we have electromagnetic flux equals negative dB dt times A. So this though, let's see. So this will be, I'm going to rewrite area. So we're going to have mu naught over 2 pi r times negative k. And then I'm going to rewrite area in terms of, so I'm going to say right here is delta r. And then this will be B. So what we're going to do is we're actually going to integrate it because the magnetic field will change with respect, the change in magnetic field with respect to time will be dependent on how far away it is from the wire. So, and then we need to multiply by B because that's the width. And this dr, when we integrate it from, I think it's d to d plus a, that will give us the height of this rectangle. So I'm going to rewrite this again to kind of get the constants out and make it more mu naught, can't forget the b, a 2 pi, we got a k and a negative, and integral 1 over r right there. And that will give us equals negative mu naught I, b, k, 2 pi. And then the integral of 1 over r is natural log. And that will give us natural log of d plus a minus natural log of d. And normally, if you have two logs that one subtract the other one, you can then divide them kind of like this. It's just a log rule. Yeah, have to know it. One way that I would remember that would be you just pick a number like natural log of 3 minus natural log of 2. And it's like, does that equal natural log of 3/2? And that's in no way a proof, but it's kind of useful because you can just throw it in your calculator. Go over here to Wolfram. So let's do natural log of 3 minus natural log of 2. I do love Wolfram. We get something like 0.405. It's going to be awkward if I'm wrong. 0.405. Okay. So I didn't by any means prove that to be true, but it's like, yeah, probably close enough. Maybe. I'm sure it is. Okay. So this is going to be the induced field, and then the power dissipated will be I squared over R. But all we have is, no, it's I squared R. I squared R, which equals V squared over R, which is natural log of D plus A over D times mu naught BK over 2 pi squared over R. And then I dropped the negative sign because we squared it, and I think it asked us for magnitude. Plus, power dissipated in a resistor is direction independent, so it doesn't matter either way. Okay. So what I did was, I was like, all right, here's the answer to the last question. Derive an expression for the power dissipated in the light bulb. I squared R, and it is this monster of an equation. I know. I hate having giant expressions, but that's kind of what it is this time. So let's see if we answered the other parts of the equation as well, or other parts of the question, which should be good. Derive an expression for the magnetic flux through the loop as a function of time. Magnetic, whoa, where'd I go? That's the problem with an infinite board. You can get infinitely lost. All right, magnetic flux with respect to time. Derive an expression for the magnetic flux through the loop with respect to time. So here is, so flux dB dt. So the flux was, I think we did this backwards. So this is a problem not following their way of doing this. So flux equals B times A. We know that B was mu naught I over 2 pi R times area, which we decided was dr from D to D plus A. So this gives us our height, times B. That gives, these two together gives us our height. This gives us our width. And so to give a flux, then we decided it was mu naught I B over 2 pi natural log of D plus A over D. And then to get it with respect to time, we're going to have to then replace that with I naught minus KT. So it would be mu naught B 2 pi natural log D plus A over D times quantity I naught minus KT. There we go. Whoop. And this is the answer to that one. I know. So we could have done the things in a slightly different order, but since we did them in the order that we did, we already basically solved it, but not explicitly solved for this portion right here. And that's how we'd go back and solve for the magnetic flux through the loop as a function of time. We took the derivative at first and then found the, not important, you'll see. Okay. Determine the magnetic field at time t equals 0 due to the current in the long wire. I probably should go the other direction. I should probably start at A and work my way down. Okay, I will. Indicate the direction of current in the loop. Okay. Okay. So for this, we'll use Lenz's law here. EMF equals negative d flux dt. So the magnetic field at this point, using the right-hand rule, at this point will be into the board, and at this point will also be into the board. And so we have a flux going through the center, and that flux, magnetic flux, I'll call this original, is decreasing because it's related to the magnetic field in the area, and the magnetic field is lowering. So this will cause an induced EMF, which will be rising. So it'll be rising into the board, and that will have to do that, you'll have to have one going, you have to have a current going clockwise. And so this will be a current clockwise, because that current will then create a magnetic field going into the board that will counter or mitigate the drop in the magnetic flux. Is that right? Now I feel, ooh. Darn it. I think I just led you astray. So, right-hand rule. Whoop, get rid of this. Outrageous. Right-hand rule. So, magnetic field goes this direction. Magnetic field coming out. So that creates a magnetic field coming out of the board. The magnetic flux, original, is lowering. So that's going to create a magnetic counter EMF due to Lenz's law, and this will be induced, going up, which will create a current going in the right. So it'll go the current here will go in this direction so as to create a magnetic force that supports the original magnetic field. So it's trying to compensate for the dropping magnetic field by creating another magnetic field that supports it. So it will be in clockwise? Counterclockwise. There we go. And then next part, indicate whether the bulb gets brighter, dimmer, or stays the same brightness over the period of time. Okay, so for this then, the brightness, that's going to have to do with power dissipation, which you already kind of found at the end. Probably should have gone through this in order. Oh well, lessons learned. So power equals V squared over R, which is voltage squared over resistance. And we know that our EMF, let's see if we can find our EMF. Oh, EMF, there we go. Here's our EMF right here. Clean this up. So this is the electromotive force, which is the voltage, and this is independent of time. So the reason it's independent of time is because even though the current depends on time, the change in current with respect to time is constant. And so we have a constant voltage, therefore the constant voltage squared is also constant, resistance is constant, and therefore the power dissipated will be constant, and therefore the brightness of the bulb will also remain constant. Determine the magnetic field at T equals 0 due to the current in the loop wire, distance R from the long wire. Alright, T equals 0, so we need to find magnetic field with respect to time. So we had a whole bunch of stuff over here. Let's see here. Get rid of that. So I think that's what we're looking for though. So green. So we had magnetic field right here. So magnetic field, this is mu naught, and then I is I naught minus KT. where I naught is some constant, over 2 pi r. And so this is giving us the magnetic field with respect to time due to the line. And then if we plug in 0 for t, we get mu naught I naught over 2 pi r, which is going to be, let's see if that's what they're looking for. Determine the magnetic field at time t equals 0 due to the current in the wire distance r from the long wire. Yep, that's it. So that's going to be B equals mu naught I naught over 2 pi r, which is different than mu naught I because I depends on time, and this is asking for at t equals 0. Okay. And then we already answered the last two. So looking at this, probably in hindsight, I should have been more careful about trying to jump to the end and then work my way backwards. Sometimes that works out beautifully, but as you can kind of see by this massive expanse of wandering, meandering calculations, it probably would have been better for me to follow the direction of the problem and just work down as the problem suggested. So when you see this problem, you first find out the direction of the current. So use Lenz's law, the voltage equals negative d flux dt. So you have a flux that's created by the wire, which is out of the board. That is getting weaker because the magnetic field is getting weaker because the current is going down. That weaker magnetic field is going to be compensated by a current that's induced. That induced current is going to create a magnetic field that reinforces the weakening magnetic field. And so to create that magnetic field to mitigate the loss, it's going to have to go counterclockwise the current. And that counterclockwise will then reinforce the dying magnetic field from the wire. And that all comes from just logically right arrows, this, that, answer. And then second guess yourself a few times because it is really easy to get tripped up. And if you do make a mistake, try and make an even number of mistakes. That way they'll kind of cancel each other out. Don't actually go for that method. Okay, so here, and then when you use the Lenz's law, negative d flux dt, you're going to take a bunch of derivatives, plug in some values, probably take some more derivatives. In this case, we actually did an integral because the magnetic field was not constant throughout the square. It was not uniform. So we had to integrate from the bottom of the rectangle to the top, which case was d distance from the wire to d plus a. And then we finally got a voltage, induced electromotive force around the wire, which gave us, we could then use to find the power that's dissipated through the light bulb. And a whole bunch of other small steps along the way. And we got a giant thing that looked kind of like this. So that is how you approach these problems. They kind of have a specific flow to them. We'll go through a few more and kind of habituate ourselves, get used to this. So these are going to be common problems that you'll see on the AP exam. You're not guaranteed to get one, but pretty much probably going to happen. So it's definitely worth studying and worth familiarizing yourself with. Okay, so that is good for today. I will see you next time.